Last year in Physics 20, we learned about 3 of Newton's laws. The first law says an object in motion stays in motion, straight line, constant speed. An object at rest stays at rest forever until acted upon by an unbalanced force. Newton's second law says the acceleration is proportional to the net force and inversely proportional to the mass. In other words, F is equal to m times a. The third law says if object A applies a force on object B, or object 1 applies a force on object 2, then object 2 will apply an equal and opposite force on object 1. These are the 2 that I want to focus on because these are the 2 that take us into our first 2 major concepts of Physics 30, which are impulse and conservation of momentum. Tell me, which one goes with impulse? Is it Newton's second law or Newton's third law? Remember, impulse meaning delta P is equal to F times T is equal to M times delta V. Okay, is that Newton's second law or Newton's third law? Remember, we derive the equations. I told you, you're not going to have to derive the equations, but I do want you to remember which law it comes from. It's the second law, yeah. So this one goes with this one. And then Newton's third law, of course, leads us into that conservation of momentum topic that we learned about on Friday. Okay, if object 1 applies a force on object 2 applies an equal and opposite force on object 1. In other words, if object 1 gains a certain amount of impulse, object 2 will lose the same amount of impulse. In other words, the total amount of momentum is going to remain exactly the same in an interaction. That is, if that interaction is an isolated system. What do we mean by that term, isolated system? Go ahead, Lewis. Yeah, in the end, it means we got no objects coming in or out. We have no energy coming in or out. What it boils down to generally is that we have no external forces. Why is that important? Well, because in the end, if you have an external force like friction, friction is going to take momentum away from the system. Okay? Now, how do we make sure that we have an isolated system? Because the reality is we almost always have things like friction, right? Well, generally what we're going to do is look at the situation immediately before and immediately after. So instead of saying initial momentum is equal to final momentum, initial is 8 seconds before the collision, and final momentum is 3.5 minutes after the collision. Okay, let's look at the initial momentum just before, like immediately before, and the final momentum immediately before. And that gives us a chance to find the momentum before any external forces have had a chance to really be a major factor. There may be external forces, okay, but we're looking at the situation before those external forces have a chance to really be a major factor, right? Once we see this, once we see our main equation for conservation of momentum, essentially what we got to do at this point is just look at, look, how many objects do we have before the collision takes place or the explosion takes place? How many objects do we have after the explosion or the collision takes place? And then we got to write down an MV term for each one of those objects. So if we have 2 objects colliding, it would be M1 V1I, object 1 initial, plus M2 V2I. If they stick together, then there's only one object after the collision, then it would be MVF. If they don't stick together, then it would be M1 V1F plus M2 V2F. We could have M67 V67 initial if we had 67 objects colliding with each other. It's not likely that's going to happen, but in the end, who knows, right? Count up the number of objects before, the number of objects after, and put an MV term in for every object. Now, one more final thing before we check our homework here. I've seen this mistake a number of times over the years. I wouldn't say it's a common mistake, okay, but it's happened more than once over the years, okay? We're looking for the initial momentum, the total initial momentum. We're going to add the momentum of object 1 and the momentum of object 2. Got that? Yeah, that seems pretty straightforward, right? In the end, what I've seen probably over the years, a dozen people do is say M1 V1I times M2 V2I. So what do you end up doing there? You end up multiplying everything together, right? M1 V1, M2 V2, M3 V3, whatever the case may be. Okay? I don't think you guys are going to make that mistake. Just be careful, okay? Make sure you don't make that mistake. We're adding the terms together as opposed to multiplying. All right. We had 2 questions for homework on page 477. We need to go over either one of those. I would assume that we have to go over something, if not all. Number 2. Can we go to number 1, or we need to go over that one as well? Okay, 1 and 2. All right. Student on a skateboard with a combined mass of 78.2 kilograms is moving east at 1.6 meters per second. As he goes by, the student skillfully scoops up his 6.4 kilogram backpack from the bench where he's left it. What will be the velocity of the student immediately after the pickup? Okay, we want to think of a few things, right? We want to see if there's anything that we should circle in a red pen. We want to see if there's any concepts that we know right away apply here. We want to see if there's anything that we kind of know, right? Just bigger picture stuff, not necessarily our givens like M1 is 78.2 or whatever the case may be, but just bigger picture stuff. Okay, is there anything here? Yep. Okay. That's a good observation. Okay, that's a good prediction as to what's going to happen, and it's a solid prediction. Okay, it's not one of those. I think this is going to happen. We know this is going to happen. The velocity of the system after he picks up the backpack is going to be less. How come it's going to be less? The momentum has to stay the same. Okay, the momentum has to stay the same. And if you got more mass, which you do after you pick up the backpack, then the velocity has to go down. So I'm just going to make a little note there that the velocity is going to decrease. How much, we're not sure. Okay, but again, that's a nice little check once we've solved the problem. Okay, if we get a velocity that's bigger, we know we've made a mistake. Okay, is there anything else there? Yep. Okay, the backpack is at rest. It doesn't physically say VI is equal to 0, right? So that's one of those things that maybe we want to just draw attention to in there. If we call that M2, then we're going to say V2I would be 0 meters per second, right? The initial velocity of the backpack. Again, guys, we're not looking for givens per se right now, but things like that, read between the line givens, sure. Is there a concept that applies here? What do you want to do? Impulse, momentum, conservation of momentum, energy? Let's see. There's a couple of things that we could do here, right? We could do impulse. We could. Or we could do conservation of momentum. If we're going to do impulse, which I'm not suggesting that you do, but you could, okay, then you got to make sure that you look at one object or the other. Pick an object. Look at its change in momentum from before to after. If you're going to look at conservation of momentum, which I'm suggesting you do, then you want to look at the system. Does that make sense? Okay. One object. Conservation of momentum is the system. Okay, I'm suggesting we use conservation of momentum here. Okay, one more little thing that I wanted to draw attention to myself, at least, as I read through this. It says a student on a skateboard with a combined mass of 78.2 kilograms. Sometimes we see those words, student and skateboard, and we want to think two objects, right? Because it's describing two objects. It's not really describing two objects, though. Okay, what do we know about the student and the skateboard? Well, we know they have a combined mass of 78.2, and we also know that the student and the skateboard are together for the entire problem. Student's not jumping off the skateboard, student's not jumping on the skateboard, they're together for the entire problem. So you know what? Let's just call them one object. Let's call that M1. What's this 1.6? It's a velocity, right? Is it V1 or V2? Velocity 1 or velocity 2? It's V1. It's the skateboard and the student. Is it V1I or is it V1F? Initial or is it final? Is this before he picked up the backpack or after? Tyler? Before. So let's call it V1I. V2I, Aiden, I think, already told me what that was. Okay, 0 meters per second. What's the velocity of the student immediately after the pickup? So we're going to say V1F. Is that what we're going to say? Yeah? Or could we just say VF? Why could we just say VF? Why don't we need the 1 in there? Yeah, Alicia? Yeah, I use the term they stick together. They stay together, right? So it's one object. Okay, you're thinking of the backpack and the student and the skateboard being one. He's one with his backpack. All right, so let's do our conservation momentum thing. We have two objects before, so we got two terms, and then we have one object after. So you got one term there. M1 is 78.2. Hey, can we cancel out that mass? Mass appears in every term, right? Can we cancel it out? Only if it's the same mass that appears in every term. Just because the letter does, doesn't mean we can cancel. V1I is 1.6. What did I just do there? What did I just do there? Yep, Jeremy? Yeah, V2I is 0, so what did I say this one, M2? M2, 6.4 times 0 is 0. If you want to write that down, go ahead, okay, but in the end, we know when we have a 0 in there in any term, then that disappears. Okay, what's M going to be here? What's M going to be? Yep, Joseph?
84.
Good. It's the combined mass, 84.6 kilograms. Solve for VF, right? All right, so multiply these two together, then divide by 84.6. And when we do that, we should get the answer that's in the book. I would assume 1.5 meters per second. Is that good? Good. All right. Let's take a look at number 2 here. It says a 1,050 kilogram car at an intersection has a velocity of 2.65 to the north. Hits the rear of a stationary truck, and their bumpers lock together. The velocity of the car-truck system immediately after the collision is 0.78. What's the mass of the truck? Anything here? Jumps out at you? I haven't really seen a red pen thing in either one of these questions because the units are pretty normal, pretty standard, right? There's no north-south. It's all one direction. So that's good. Okay, those things that can lead me to a silly mistake like that, I think are, pretty much out of the question here. We know it's a conservation of momentum problem, or we could use impulse. But if we're going to use impulse, we've got to pick one object or the other. I think it makes sense here to use the system, conservation of momentum. Aiden would tell me right now that the truck is stationary. So he would tell me that V2I would be 0, right? Okay. Good. Another thing that it's not a huge thing, but it's important, okay? It might be something that we want to draw attention to a little bit. I don't think it's worthy of the red pen, but hey, these bumpers lock together. What does that mean? Nathan? It becomes one object afterwards, right? Okay. The truck becomes one with the car. All right, let's identify our givens here. I think we got this now. This is going to be M1. We're looking for M2. We've got V1 initial. V2 initial is 0. And we've got, what's the 0.78 thing here? V1 or V2? It's just VF, yeah. Because they stick together, right? Same as it was in the last one. All right. So we got PI equals PF. We've got M1 V1 initial plus M2 V2 initial, two objects. One object afterwards MVF, same as the first question, right? This disappears again, same as it did in the first question, because one of them was at rest. M1 is 1,050. V1 initial is 2.65 equals M. We don't know what M is, do we? We don't know what the combined mass is. Okay, the mass 2, whatever it is, times 0 is 0, but whatever the combined mass is times the final velocity isn't 0. Anybody have the value for M there? I'll give you a hint. If you haven't found it yet, it is not 2.5 times 10 to the 3. 3,570. Okay, thank you. It is a multiple choice question. You can be sure that that's one of our options, right? Okay, what are we looking for here? Not 3570, not the, what was this? What did this represent? Yeah, that's the combined mass, right? What are we looking for? Yeah, looking for the mass of the truck. So we're going to say the combined mass of 3570 equals the mass of the car plus the mass of the truck, M2. And M2 now works out to be 2.5 times 10 to the 3. Is that right? Are we good there? Adam, is that okay? Our next question, our example on page 478 says a basketball player and her wheelchair have a combined mass of 58 kilograms. She moves 0.6 to the east, pushes off a stationary player while jockeying for position near the basket. Player A ends up moving to the west. The combined mass of B and her wheelchair is 85 kilograms. What's player B's velocity immediately after the interaction? There's quite a bit to sift through here when you're reading. It's not a crazy hard question, but there's kind of a lot to read through. What do we got? Well, it's a collision, right? Okay, somebody pushes off. It's like a collision. So we're going to say conservation of momentum applied. That's the main concept. That's the most important thing that you can identify. Or we could do impulse if we picked one object or the other. I'm going to pick up the red pen for this one, though, because I see something right now. I want to circle here. So what is it? Yeah, I got an east and a west, so probably going to make this one negative, right? Draw attention to that, so you're less likely to forget. Aiden, going to call on you because I know you know this one. Yeah, we're going to make it V2I, 0 meters per second, right? V2I, because we'll say the first player is the person that was moving at 0.6. The second player was at rest. You know what kind of bugs me a little bit about this? It just in terms of wording, the combined mass of player B in a wheelchair. It says what's player B's velocity? Like it's almost kind of trying to trick us, trying to confuse us into thinking the wheelchair is an object and the player is an object, right? The combined mass, that word combined even, kind of suggesting to us almost that two separate objects here. But the reality is they're not. Each player stays on their wheelchair, doesn't get off, doesn't get on. So a player and her wheelchair is an object. That means that this is going to be M1, this is going to be V1 initial, V2 initial is 0, what do we got here? Player A ends up moving. Okay, be careful, you get the right player. Player A ends up moving at 0.2. That's going to be V1F. Look, we got to look way down here to find mass 2, or player B's mass. I think that's it, isn't it? Looking for V2F, the velocity of player 2 afterwards. Man, I get stuff everywhere here. One of these questions, maybe it even makes sense to write down your givens like you did in Physics 20, like list them. Whatever works for you, though. Caitlin, how many objects do we have before the collision takes place here? 2. We got 2 players and their wheelchairs, but the wheelchairs are with the players, right? So we're going to say 2 terms, M1 V1 initial plus M2 V2 initial. How many objects do we have after the collision? Michaela, how many we got after the collision here? We have 2, right? This time we have 2. Okay. In the problems we did for homework, we had 1 object afterwards in both cases. But here, they push off. They both go in different directions here. So we're going to say we have 2 objects, M1 V1 F plus M2 V2 F. Now we got a term for each of those objects, right? Okay. Hey, listen, if we got lucky on this, then the mass of both basketball players and their wheelchairs would be the same. If that was the case, we could cancel masses. But we can't, because they're not the same here. Get 58 times 0.60. That disappears because V2I is 0. If you want, you could even avoid writing that down in the first place, right? If you recognize right away that there is no momentum there. V1F was negative 0.20. I'm not going to forget that negative because I drew attention to it with red. Although I'll tell you, if you don't draw attention to it, man, how easy would it be to forget to make it a negative with all the wording in this question? M2 is 85. V2F is, that's what we're looking for, right? Uh, 58 times 0.6, 34.8. I got 58 times negative 0.2, negative 11.6. .6 goes over to the other side by adding. What is that going to give me? 46.4. And we're going to say 46.4 divided by 85 gives me 0.545. 0.55. Yeah. So maybe there's some time in your life you're going to be watching people playing wheelchair basketball, and you're going to want to pull out your calculator and your pen out of your pocket protector and determine how fast the second player is moving immediately after the collision. Maybe you will want to do that sometime. Probably not, but maybe. Okay. Is there ever a situation out there where maybe in your life you would actually want to use this conservation of momentum to calculate something? Well, I'll tell you what. If you become a sandwich artist at Subway, you're probably not going to do this. Okay, you're probably never going to use this. Okay, if you decide you want to be an English teacher, you're probably not going to use this. Maybe you're an engineer. Maybe you're a police officer. Where would a police officer ever use something like this? Maybe you had an accident. Probably not calculating the final velocity. You'd probably determine the final velocity from skid marks, and then do what? Maybe you want to calculate the initial velocity. How fast was the car moving? In other words, was the car speeding before the collision took place? Okay, exactly the same thing, except you're solving for a different variable, that's all. All right, let's see what we can do with these two questions on page 478, please, at your desks. Okay, let's take a look at number 2 here. It says 9,500 kilogram flat, can't speak, can't read this, a 9,500 kilogram rail flat car moving forward at 0.7 strikes a stationary 18,000 kilogram box car, causing it to move forward at 0.42 meters per second. What's the velocity of the flat car immediately after the collision if they fail to connect? Okay, what does that mean, they fail to connect? Okay, what are they really telling us there in terms of physics? Okay, Alicia? Yeah, we're going to have two objects afterwards. So it's like the example problem that we did a few minutes ago, right? You got one object colliding with another object that's not moving, and then after the collision, they're both moving. So we've got m1v1i plus m2v2i equals m1v1f plus m2v2f. Anything else here? Red pen? North, south, east, west? Both of them are forward, I think. Yeah, I think everything's forward, so we don't have to worry about direction there. We can make them both positive. Conservation of momentum, right, because it's a collision. Or technically, we could use impulse if we looked at one of the objects. Let's call this M1. Let's call this one V1 initial. Let's call this M2. Let's call this V1 or V2? Yep. This is going to be V2, and it's going to be V2F, specifically because it's object number 2 after the collision takes place. We're looking for V1F, the velocity of the flat car immediately after. Was there anything there that, reading between the lines, I probably should have thought of this before I wrote down my givens. Any read between the lines? Aiden, you're the guy today for this. Any read between the lines givens that we don't see in so many words? Okay, so the boxcar was object number 2, and it was initial, right? 0 meters per second. All right, good. PI equals PF. We said a few minutes ago, M1, V1, initial. You know what? I'm going to leave that term out this time. Up till now, I've been crossing it off because V2I is 0. But if V2I is 0, I don't even have to put that term in if I don't want to. M1, V1F plus M2, V2F. I got to put both of these in there. M1 is 9,500 kilograms. V1I is 0.70. V1F was, that's what we're looking for, right? M2 was, what is it, 16,000 or 18,000? 18,000 times V2F was 0.42. All right. Stay with me on this one, okay? Because I know as I was walking around when you guys are working on these, a couple people were having trouble rearranging these ones. We're going to multiply 9,500, first of all, by 0.7. 6650 equals 9,500 times V1F plus 18,000 times 0.2. 0.42, I mean. 7560. Okay, what's next? What's next in the whole process of rearranging this one to solve for V1F here? What's next? Allie, what do you want to do next? You want to get rid of the 9,500? Do you want to get rid of the 7560? Yeah, and how are you going to get rid of that? Good. Get rid of what's not multiplied or divided first, okay? If it's added or subtracted, get rid of that one first. So 6650 minus 7560 gives me negative 910 equals 9,500 times V1F. And now how are we going to get rid of a 9,500? That's just a division, right? So 910 divided by 9,500 gives me 0.096. And notice it's a negative value, which is exactly what we should get there. Okay? Good there? All right, I want to do one more example for us here, okay? One more example for you here, and that's the last one that I want to do for you today. Page 479, it says 110 kilograms Stampeders football fullback moving east at 1.8 meters per second on a snowy playing field is struck by a 140 kilogram Eskimos defensive lineman. 140 kilograms, eh? Like, that's heavy. That's a big boy. Yes, it is. I weigh 70 kilograms. That's literally twice my mass. Literally twice my mass. And I have a feeling, I'm 6 feet tall. I have a feeling this guy's not 12 feet tall. So if he's twice my mass and not twice my height, he's a little bit wider than me, perhaps. Maybe a little bit thicker. Moving west at 1.5 meters per second, the fullback is bounced west at 0.250. What's the velocity of the Eskimos defensive lineman just after impact? Concept, red pen, read between the lines stuff. Okay, just general awareness. What do we know stuff? Tell me something. Yep. East and west, yeah. East and west. Okay, we got an east here, we got a west here, and we got a west here. Units are all good, I think. Meters per second, kilometers per hour, meters per second, kilograms. Concept is conservation of momentum, right? I'll give you that one because we got a collision. Every time we have a collision, we might as well try that. I think that's pretty much it, eh? Nothing else real confusing about this. It's gonna get a little cumbersome here, as it does sometimes with these if I just circle give it. So I'm gonna write them down like we traditionally did in Physics 20 this time. Okay, how you do it is up to you. I'm gonna say 110 kilograms is M1. I'm gonna say V1 initial is 1.80 meters per second. I'm going to say M2, that's the Eskimos player, is 140 kilograms. He's moving west initially, V2 initial, at negative 1.5 meters per second. Negative because it's to the west. The fullback, who's the fullback? Stampeders or Eskimos? That's the Stampeders player, right? So that's going to be V1F. V1F is negative 0.250. I'm not going to forget the negative because I circled that. And we're looking for V2F. What do we got? Two objects, M1, V1 initial plus M2, V2 initial. I'm not going to just scratch one of those out because they're both moving, right? Two objects afterwards as well, M1, V1F plus M2, V2F. Don't forget the negative there. Negative again because it's to the west. Okay, let's go through this one, the rearranging of it, because if you're having a little bit of trouble with the last one, rearranging it, then you definitely have trouble with this one. 110 times 0.8, or 1.8, I should say. At 198. 140 times negative 1.5. That's negative 210. Let's just subtract 210 from that. Plus negative 210, or just subtract 210. Now we got 110 times negative 0.25, negative 27.5. All right. What do you want to do first here? What do you want to combine first? Tiffany, what do you want to try first here? Combine the 27.5 with the other side? Good. Let's do that. So do a couple things at once here. 198 minus 210 gives me negative 12. Negative 12 plus 27.5, right? Negative 12. Take it over by adding because it's a negative value. Becomes, what is that, 15.5? Is that right? And then we're going to take the 140 over by dividing. What does that work out to be? Do the math there, works out to be 0.111 meters per second. Good. Hey, what's really, fundamentally, what's different about this question than the other questions we've done? Okay, that's a good thing to ask yourself too sometimes when you're doing these questions. Hey, what's red pen worthy? What's the concept? What are some of the other things? Okay, what's a difference between this question and the questions we've done? What's similar about it? What's different about it? Yeah? Yeah, both the objects are moving, right? That's what's different about it. But really, it's the same question, right? I mean, there's a little tweak there, but fundamentally, it's the same question. All right. Let's try those two questions on page 479, please.